I was trying to put too much through. I had 4K video trying to go through a 720 pipe. So that's what happens when you don't think about everything. But I got it covered. Okay, so for those who are joining in on YouTube, I'm live, but we're just getting set up. So I think I got the I am not expecting any of those yellow errors. Do your attendee limit on Eventbrite? Uh-oh. Gotta check Eventbrite. Brian Duncan just sent me a text. Do your attendance attending other PDHs? Brian Duncan. Okay, Brian Duncan. So I have a limit of 1,000 people on Eventbrite. I hope I have to exceed. I have to bump that up. Smiley face. I will be doing PDHs as well. So I am next week, excuse me. Next week I am doing 2020 code changes. I think on Thursday, I got to check. I haven't heard from my customer yet, but I might have to do a customer webinar. But if not, on Thursday, I am going to be doing Breaker Basics. Breaker Basics this time. If I do have to do a customer presentation, then Breaker Basics will be either in the morning or in the afternoon. Stay tuned for that. But I'm planning to do. I mean, the PDH thing is cumbersome in the evenings. I try to get all those certificates made, but I'm getting them done. So. Awesome. Gotta move. That's right. I can't put the chat over there. Got to put it. Can't put it up there either. I gotta put it down here. Good morning, Nihad. I appreciate you dialing in early every day, buddy. You are awesome. That's the thing. Since I'm broadcasting, the people on WebEx can't see the chat when it comes up over there, but the people on YouTube can. So I got to move that. I got my desk. I need a bigger computer. I got an excellent connection, so now let's do a test. I am going to do a test. I need to get the folders. So if I just double click on this, yes it does. All right, so I'm going to come over to the WebEx, and I am going to share out a different screen. I don't know how fast that works. I am going to have my YouTube friends go to screen 2 and watch a short, hopefully a video if it doesn't clobber my drive.
There was a time not too long ago that people didn't wear seatbelts. If you got in the car with your buddy and you put your seatbelt on, but your buddy didn't, it was an uncomfortable feeling.
What's wrong, Mr. Safety? Don't you trust my driving?
Today we wear seatbelts for 2 reasons. 1, it's the law, but 2, it's been proven that seatbelts save lives.
Arc Flash Safety is evolving in a very similar way. You may walk into a situation where you are probably wearing a 40-calorie suit and you are working side by side with someone in a t-shirt. Who's right and who's wrong?
Just like the seatbelt example, it's an uncomfortable feeling. But since arc flash safety is now required by many companies, and the safety governing bodies like NFPA and OSHA have new standards, the electrical industry is starting to pay attention and do the right thing. How can you ensure that you're doing everything you can to keep your employees safe? Here at the Power Systems Experience Center, you can learn about arc flash safety and the solutions that exist to keep you and your people safe.
So what is an arc flash? An arc flash is an unintentional release of energy caused by an electrical fault. An arc flash event can reach temperatures of 36,000 degrees Fahrenheit, or 4 times the temperature of the surface of the sun. During the arc, copper can expand at 67,000 times its volume, very much like an explosion caused by dynamite. And if you're as startled as you would be in the case of an arc flash event, you would quickly inhale and breathe in that vaporized copper. About 2,000 arc flash incidents are reported each year, and as you can imagine, it is likely the actual number is significantly higher as workers are embarrassed or fearful of losing their jobs if they report a near-miss incident involving an arc flash.
Arc flash energy is measured in calories per centimeter squared. An arc flash label has 2 critical pieces of information on it: the calories per centimeter squared, or the energy released, and the distance that a worker would have to stand outside to avoid a non-curable burn if an arc flash were to occur. If you held a match 1 inch under your finger for 1 second, that would be approximately 1 calorie per centimeter squared, or just below 1.2 calories per centimeter squared, the amount of heat that would be required to cause a 2nd degree burn, which is the limit of what we call a just curable burn. As you can imagine, if you pulled your finger away quickly, as you would do when you touched a hot stove, or if you held the match 10 inches away, there would be less heat. This illustrates that time and distance are critical and somewhat controllable variables. Similar to an arc flash event, if we can control the time and distance of the arc flash, we can lessen the impact. Here at the Experience Center, we can show you options that reduce the time of the arc flash event and increase the distance of the worker to the location where the arc flash occurs.
This arc flash label indicates that the arc flash energy is 27 calories per centimeter squared. So in order to protect a worker from this amount of energy, they would have to wear a 40-calorie suit, like this one. A worker dressed in an 8-calorie suit would not be protected from a 27-calorie event. The clothing effectively acts as a thermal barrier to the arc flash event, protecting the worker from the thermal energy at a working distance of typically 18 to 24 inches. The second critical piece of information on this label is distance. This label shows that in order to avoid a 2nd degree burn, a person without arc flash personal protective equipment, or PPE, would have to be 18.5 feet away. The only way to operate on equipment from this distance without PPE is to do so with some type of remote control device or equipment.
These labels are created by our Power Systems Engineering Group, using models of electrical power distribution equipment data from your site with the sizes and settings of your protective equipment taken into account. This ensures that the calculated arc flash levels are accurate for your situation. Our PSC group has done thousands of arc flash studies and applied solutions for our customers' facilities and our own. The NFPA 70E standard serves as a guide defining the method that companies should use to perform arc flash analysis, labeling, and training of personnel. OSHA has used the NFPA 70E in the past, following a reported arc flash incident, but more recently has been proactive in their approach to arc flash safety. In 2015, OSHA released a final rule requiring that companies that own and/or operate their own power system equipment perform arc flash calculations and apply labels to their equipment. In addition, it requires that companies provide PPE and training regarding arc flash safety.
Eaton has nearly 100 solutions for arc flash safety. And here at the Power Systems Experience Center, we can introduce you to all of them. We focus on opportunities to reduce the arc flash energy by reducing the fault current, reducing the clearing time, and increasing the distance from the arcing fault to personnel. For example, this gear is to do everything with the door shut, like this self-racking mechanism in our medium voltage resistant switchgear. The most common type of arc resistant switchgear is type 2B. With 2B medium voltage arc resistant gear, the low voltage metering, relaying, and control compartments are isolated from the gear with a separate door.
One of the most common times for an arc flash event to occur is when adding or removing a bucket in a motor control center. This flash guard bucket can be added or removed with the door shut, with a local or remote operator protecting the worker until the bucket is safely removed from the energized bus. This FlashGuard MCC takes the procedures and guesswork out of your hands, only allowing the disconnect from live bus operation to be done exactly the same way each and every time.
This low voltage assembly illustrates a very common yet very dangerous situation. The arc flash label indicates that the arc flash energy on the primary side of this breaker is 68 calories, well above the maximum allowed when wearing a 40-calorie suit. Yet on the secondary side of the breaker, it is only 14 calories. For a fault on the secondary, this breaker can trip quickly. For a fault just on the other side of this breaker, even though the fault current is the same, the energy is much higher because the clearing time of the nearest upstream device is intentionally delayed to compensate for transformer inrush and coordination. So how could we create a selectively coordinated system that compensates for the expected transformer inrush, but at the same time clears a fault on the line side of this main breaker quickly enough so that the arc flash energy levels are substantially lowered? Our VCPT solution allows us to use a medium voltage vacuum breaker and 2 protective devices to detect faults in different zones around this transformer. The most difficult fault location being the line side of this main breaker. With this solution, this medium voltage breaker can selectively determine how quickly to clear a fault, significantly reducing the arc flash energy to well below 10 calories during maintenance conditions. Arc flash safety is one of the most important issues facing our industry today. We can help you comply with the latest NFPA 70E and OSHA requirements by showing you options for analyzing your power system, applying labels, and training your people to minimize your risk of arc flash incidents.
As you can see, there are many things to consider when determining the arc flash level and methods of reduction for your power system.
Here at the Power Systems Experience Center, you can see the latest in arc flash mitigation techniques and learn about solutions that can help you with your arc flash safety program.
Contact us or your local Eaton representative to schedule a visit to the Power Systems Experience Center today.
Now that is cool. I don't know about you guys, but I figured out my settings, and but now I just have to figure out how to get, there you are, sharing that screen. I'm going to share a different screen now. I'm sharing content for the, so I got 2 things going on here. So awesome. So we got, I have good signal strength on my YouTube channel. I can't believe I figured a video out. I just have to figure out the, I have to get the audio. I think I sound a little distorted on YouTube. So Santino, thank you. Unless you're trying to do auto tune for singing purposes. What? Thank you, James Mercier, for sitting with us on YouTube. I appreciate it. So just your voice when speaking sounds a little robotic. I wonder what the heck. Yeah, Ryan, I tell you what, Ryan, it is, this has been a journey for me to try to figure out how to do a live broadcast. I'm not as quick of a learner as many because what? It took me Monday, Tuesday, Wednesday, Thursday, and here it is Friday. I am finally getting, I'm not getting any yellow problems and hesitations in the video. So we got 20 people dialed in on YouTube.
Is that Minty code for today that you're showing on your screen? And if so, on the Minty website, it's referencing AFCI and the NEC.
Oh, that's not the right code then. Wait, hold on. Let me look at my entry. I think, you know what? I think it is the right code because, man, see, this is what happens when you've got all of my people. I'm firing the one who did that class attendance. I'm going to fix it. I'm fixing it right now. Here, you know what I'll do is show you guys how I fix it. That sounded like whoever it was on, I use Mentimeter. So if anybody who's a teacher out there, Look at that. It says AFCI and the NEC. So here's how we fix that. Class attendance, I changed this to safe work practices, and then it automatically saves. And then when I hit home, I'm actually it's automatically there. So, and then I just have two things. You make sure the last page doesn't say. See, that was easy. I gotta have an easy button. All right, thank you, whoever that was. I'll call you the Almighty. It was like a voice. All right, so let's do. I'm gonna share the Menti screen again. For those of you on YouTube, you're looking at the bottom of my chin because I moved everything up. I had my monitor directly behind my computer, which is not a monitor at all. It is a TV. I stole a couple TVs from around the house, and so I have two big screen TVs and my computer. And then another little word, Ryan, to do. I don't know how you do it, but I have 1, 2, 3, 4 books I put my computer on to lift the computer because I had a webcam and I never used it, and now I can't find it. So that's the way that goes. All right, so the stream is, man, the stream is beautiful. Can't believe it's actually worked out. I'm showing the code for Mentimeter 788914. I wrote that down over here. I have that set up, so I have an intro. You know what? I'm going to play the intro for the YouTubers. I'm not going to play the intro for. Actually, I could play the intro. I'm going to play the intro because now I got I figured it out. Word to the wise. I know. I believe Ryan. Ryan is. Here's a trick, Ryan. I think my resolution or whatever it is to 720. I think it is called. I set it to 720, and you can't stream a 4K video through a 720 pipe. I'm just saying. I figured that one out. Took me a little bit, but my videos were way too high resolution, and when I tried to play them, I think everybody was just the internet was just killing it. So I redid the video in 720, and now I can do videos. So, and that reminds me of another video, which is my favorite product, one of my favorite products. This is my favorite technical product. I'm going to queue up 2 for the web streamers. I'm going to share content, share screen 2 for my web axers, and here we go. I think hopefully you guys will like this video.
Hey, John.
Hey, Eric, how you doing?
Pretty good. Thanks for stopping by.
Oh, no problem. What do you got?
Okay. What I'm looking at here is we have the sold switchgear with an arc flash level of 68 calories. Management wants me to come up with a few solutions. There was an arc flash event at our Kansas facility, and it was very expensive.
We've talked before about the numerous arc flash solutions that Eaton has, but you might want to take a look at the arc quenching gear if you're going to replace the whole lineup at this point.
Sounds interesting. Give me the info and I'll take a look at it and pass it along. I'm not sure what they'll say, but I'll get back to you.
There you go. I did bring you some information. You might want to stop by the Power Systems Experience Center in Pittsburghville when you get a chance to see it in action.
Okay, sounds good. Thanks, John. I really appreciate it.
Sure.
Hi, my name's Adams Baker. I'm the product manager for Eaton's low voltage switchgear. Here at Eaton's Power Systems Experience Center, we have a demonstration of our arc quenching switchgear. It's a new electrical safety solution that has already revolutionized arc flash safety. So in general, how does it work? In a typical lineup of arc quenching Magnum DS low voltage switchgear, we utilize wired point sensors installed throughout the equipment that will detect the flash of light from an arc flash. And we also use CTs on the incoming line that will detect a rise in current during a fault. You can see a point sensor up at the top of the incoming cable compartment, for example. There's also one at the bottom. There are 3 more point sensors located in the bus compartment and, importantly, point sensors located over the finger clusters of all of the draw-out devices. The locations of these point sensors are tested and validated at a high-powered test lab during actual arc flash events, so we know that regardless of where an arc flash initiates inside the switchgear, we'll be able to detect it. For this demo, the yellow chasing rope lights show the normal flow of current in the switchgear. The current comes in through the incoming line, flows into the line side of the main low voltage power circuit breaker, out the load side, down the vertical bus, and then out into the horizontal bus, which would be distributed out to additional sections of feeder breakers. And you'll notice that it appears someone left a wrench magically levitating over that uninsulated bus bar. Let's lower that wrench onto the bus bar to create an arc flash and see what this system does when there's an arc flash inside the switchgear. I'll lower this wrench down onto the bus. Oh, big arc flash. Now you'll notice the blue chasing rope lights have illuminated. All of the current is now flowing into the blue arc quenching device. It's no longer flowing through the wrench, which initiated that arcing fault. So the arcing fault instantly extinguishes because all of the current flows into the arc quenching device. That actually occurs in a total of 4 milliseconds. That's at less than a quarter of a cycle. It takes about 2 milliseconds to detect the arc flash, which is done by the Eaton arc flash relay and those arc flash sensors that I pointed out, and another approximately 2 milliseconds to commutate that arc energy and contain it inside the arc quenching device until the main breaker opens up and de-energizes the lineup about 3 to 4 cycles later. So if you had an arc flash event, all you need to do is go up to the equipment, which is now de-energized. The relays will indicate which point sensors saw the arc flash, so you know where to go in the equipment to find the cause of the fault. You'll remove the cause of the fault and inspect the equipment, and then return it to normal operating condition, which should be relatively easy, since the equipment will be protected from damage due to the quick reaction of the arc quenching system. And then you'll rack out the arc quenching device. It's a one-time use device, sort of like an airbag, and you'll replace it with a new one. If you don't have a new one on the shelf, that's okay. Once you clear the fault, you can still re-energize the lineup, but you won't get that 4 millisecond arc quenching time. And once you get a replacement arc quenching device, you can actually rack it onto the energized bus and be back up and fully protected. So with your skilled workforce, or with Eaton's engineering services on site, you can potentially have a lineup of switchgear recovered from an arc flash event in a matter of hours, instead of weeks or months, which may be required to repair or replace a heavily damaged lineup. In summary, Eaton's arc quenching switchgear is an incident energy reducing system. It can actually reduce the incident energy to less than 1.2 calories per centimeter squared. So this enhances safety, it enables the switchgear to exceed the arc resistant test requirements in standard construction without the need for ducts, plenums, thicker gauge steel, and the special construction that you normally expect with arc resistant equipment. And it even provides arc resistant protection when the doors are open or panels are removed. It also protects the equipment itself from damage, unlike arc-resistant equipment, where the internals can be destroyed. And since it protects the equipment from damage, it can dramatically reduce downtime in the event of an arc flash. By now you must be wondering how the arc quenching device actually works to extinguish an arc flash inside the switchgear. Shown here are the internals of the arc quenching device. As you can see, there are 2 arc containment vessels inside. What's shown here are actually cutaways. Each vessel is about 7 inches tall, about 5 inches in diameter. They look a little like vacuum contactor bottles, but they're not. They're actually filled with atmospheric air because under certain circumstances, we actually want arcing to occur inside these vessels. You'll notice at the top of the left vessel, we connect phase A. At the top of the right vessel, we connect phase C. And to the bottom of both vessels, we connect phase B. And each of the phases is connected to contacts, shown in tan on this diagram. If this were a bolted fault device, one way to make it work would be to clap the contacts together whenever an arcing fault is detected. This would tie all 3 phases together in a zero impedance fault, which would divert all of the current from the arcing fault into this device, immediately extinguishing the arcing fault. But of course, we didn't want to create just another voltage fault device, because such devices run the risk of damaging the upstream power distribution equipment via the massive electromechanical forces that are created when they operate at full fault current. So instead, these tan contacts are actually fixed in place. The air gap between them doesn't change under any circumstances. Under normal operation of the switchgear, these contacts are far enough apart that there's no arcing across them. You can even high pot or dielectric test the equipment with the arc quenching device installed, and it will not cause the switchgear to fail the test. But under certain circumstances, we want to be able to create a lower impedance current path inside the arc quenching device in order to extinguish an unintended arcing fault. And the way we do that is by creating a fully contained lower impedance arcing fault inside each arc containment vessel. The arcing fault is created by using a trigger ribbon. It's essentially a wire. The ribbons shown here in blue run up the side of each of the lower contacts, across the top of each contact, down the side, and then they double back on themselves and return to the trigger board. So when we want to create a lower impedance current path to divert the arc energy into the arc quenching device, all we do is pass current through each of the trigger ribbons. As you may recall from physics class, when current flows through a wire, it generates a magnetic field, also called the Lorentz force, or a B field. And you can use what's known as the right-hand rule to determine the direction or flux of that magnetic field. So the current flows up the side of the contact, across the top of the contact. We'll call that a counterclockwise magnetic field. It goes across the top, down the other side, and then it doubles back on itself. And we have a clockwise magnetic field. In a matter of microseconds, we have created two opposing electromagnets in the wire. That causes the top half of the wire to be repelled from the bottom half, and it jumps up and hits the top contact. The trigger ribbons momentarily tie phase A to B and phase C to B. But the trigger ribbons are too thin to be able to conduct the available fault current and voltage, so the ribbons melt, they vaporize, and then they ionize. And when you ionize copper, you create an arcing fault. So we have spontaneously created two arcing faults that tie all three phases together. And that's how we create a current-limited, lower impedance current path, so that all the arcing energy flows into the arc quenching device and ceases to flow into the unintended arcing fault. But by now you're probably asking yourself, how can I be sure that this is always going to be the path of lowest impedance? Because we're actually introducing some impedance by creating a secondary arcing fault. Wouldn't it be possible to introduce too much impedance so the current wouldn't all flow into the arc quenching device and would still feed the unintended arcing fault? Fortunately, the answer is pretty simple. First of all, UL 1558, which is a UL standard for metal enclosed low voltage switchgear, states that the minimum distance between exposed power conductors is 1 inch. So that means inside our switchgear, all of the uninsulated bus bar and other power conductors are at least 1 inch apart, and in most cases far more than 1 inch apart. So by making the contacts inside the arc containment vessels less than 1 inch apart, when we create an arcing fault across them, the laws of physics guarantee that the arcing fault will be lower impedance than any arcing fault that could occur across exposed power conductors inside the switchgear. Second, typical arc faults will eventually self-extinguish. That is, if you ignite an arcing fault inside any piece of equipment and supply it with current and voltage for an unlimited period of time, the arcing fault will self-extinguish. The equipment will first blow up and blow apart, and then the two conductors across which the arc is occurring will melt and vaporize far enough apart so that the arc can no longer.
You'll get a notice on that on the opportunities for next week as well. That's your code 788914. That's for signing in. This is what we use for getting all of the. I'm using this for the PDH effort that I do in the evening, and time consuming, but very well worth it. Happy to do it. So we are going to talk about safe work practices today. And I'm just queuing everything up above while you're looking at the Mentimeter. Write that number down. We are going to, we're going to move right into it. Make sure you have your 70E. I'm sure everybody has their 70E book, and it's all tabbed, and they're ready to talk about safe electrical hazard awareness. That's sort of what I'm focusing on in this session is electrical hazard awareness. So that is the title of our session. All right, so as usual, your everybody who's on the phone has been muted, except me. I took the tape off. I'm good to go. Also, there is a 70E. Again, I said the version I'm looking at is 2018, so I have the 2018 book in front of me right now, and that is a part of what I'll be. Anything if I start talking about if I quote anything from the 70E, it is going to be based upon the 2018 version. And I do, and at the beginning of each of these, I should say that I am speaking on these are my opinions. These aren't I do sit on code making panels 2 and 10 for the National Electrical Code. I sit on 70B for equipment maintenance. I'm on various NFPA documents, but I don't speak on behalf of NFPA. I don't speak on behalf of any of the members on any of the committees. These are my opinions and my opinions only. Please, if you're free to disagree with anything that I say. Use the chat in the stream. Use the chat session on the WebEx to share your thoughts. That's how we all learn together, right? I must say that I won't be looking at the chat again. I'm literally not going to look at the chat until until we get to a certain point. It's just too distracting for me. So in any case, these are 3 organizations that I have to say have helped me throughout my career, and I think that hopefully they will help you in your career. IAEI, the International Association of Electrical Inspectors, the NFPA and IEEE. These are the areas where I've built my network and all of the relationships I have that help me answer questions and do my job well. So please just take this as a word of advice. These are 3 organizations that you should be members of. IEEE, especially if you're an electrical engineer. But every one of us should be an NFPA member and an IAI member. So today's program is on electrical hazard awareness. So we're going to be talking about all of the great things around electrical hazards, raising the awareness, and again in true, excuse me, in true format. I am doing this in the question quiz results, and so we're going to be talking quiz results. And I was a little worried because I got it out very late last night. And I was also worried because I was sort of multitasking as I was making the questions. But I think I did okay, and we're going to see what you think about that. So I am going to talk about the first question, which is the 3 electrical hazards, and you had A, B, C, or D to pick from. So I'm doing this a little differently today. So I'm going to actually, share some different content out while we're doing these. So this is the survey respondents said, and I'm learning that I need to throw one gimme out there, and the first one, I guess I shouldn't give that away, but the first one is probably going to be my gimme. 86 of you said arc flash, shock, and arc blast. That is the right answer. Those are your 3 electrical hazards that we have to think about. It's arc flash, shock, and arc blast. And those who did not take this quiz, if you go to menti.com and you use the code 844696, so you can do this on your phone while you're watching it on your computer. If you're watching this on YouTube on your phone, you can go to your computer. You can even open up a different browser on your phone. I may not be technically savvy to do that, but I know some people who do it. But you can actually go through and start taking some of these, which I see people are right now. I'm up to 122, and you can self-propel through this. So as you'll just continue to go through. So I'm talking a little bit just so that people will start answering these questions. So that is. It looks like you guys are doing a good job with regard to understanding the hazards. So now I want to go back to our slide deck because Go back to this and get me out of the picture. An arc flash, there are three hazards. You have the arc flash hazard, you have the electrical shock. It's hard for me to show things on shock because they are disturbing. There are videos that I do have when I do an in-person presentation on this topic, but I am not going to do that on YouTube. I can't see my audience. I can't make a judge of that. But in any case, the arc flash incidents, and from a definition perspective, in the codes and standards world, we're all about definitions when there's a term. And arc flash, unfortunately, is one that is not defined anywhere. So when there is no definition, I mean, there's definitions for, arc flash hazard. There's definitions for all of these different terms. They use arc flash as an adjective, but not as a noun. So when you don't have a definition, what do? You make one up. And that's what I did. So I basically sat down and said, in my opinion, an arc flash is a compilation of a lot of different aspects: light, heat, sound, gases. And when you see an arc flash event, they are very dramatic. We do arc flash testing, and we'll do these demonstrations in our classes with the busman team down in Ellisville in St. Louis, Missouri. And that's where we did the testing for IEEE 1584. But this video, to me, it demonstrates the key aspects of an arc flash event. You have the light, you have the heat, you can see those molten metal, you can see you vaporized metal, and you created that big, large cloud that unfortunately many people breathe in. And the amount of energy that we release is dependent upon two key factors. And there are other factors, obviously, but there are two key factors that will impact how much energy we project, and that is current and time. It's how much arcing current I let flow and how long I let it persist. And that is a very critical and important thing to remember from a hazard awareness perspective. It's just like if you were in my short circuit class on Monday, we talked about short circuit current ratings. And I explained and I likened a short circuit current rating to a weightlifter. And we said, if I was a weightlifter and I said I can bench press 500 pounds, when spotted by Lou Ferrigno, then I know that I can, please mute your phones. God darn it. Please mute. I'm hearing somebody. Check your microphones. All right, for the guys on WebEx, this is what I'm going to have to do. I'm going to have to stop sharing. This is what we do when we have a naughty guy or person in the audience. We go to participant and we say mute all, and then we go back and we share our content, and we continue on with our regularly scheduled program. So an arc flash is all about the amount of current and the amount of time that I let that persist. And this next video, or next 3 videos, are going to really help you understand that that when I can reduce the clearing time, I can impact and reduce incident energy in a very significant way.
We'll never trip that breaker and put ourselves
Wow.
on it. Perfect.
So that video really shows and demonstrates even the aspect that third electrical hazard, which is the blast, right? There's force associated with this. If you think about the amount, the temperature at that source was upwards of 35,000 degrees Fahrenheit. You vaporized copper, we vaporized the plastic and any aluminum that was in there. It just vaporized, and anybody in and around that area, the first thing that when you shock somebody and you startle somebody, it's that initial breath that you breathe in that causes damage inside your lungs. But that is a violent event and demonstrates a lot of what an arc flash event is. Now, if I think about that mannequin that we had in front of that equipment, Anything that you see in this screen that has a greater than symbol on is basically tells you that the meter was pegged. So the temperature was pegged at his neck at 437 degrees Fahrenheit. It was pegged at his hands at 437 degrees Fahrenheit. It was the pressure, the amount of pressure that blast that we experienced was pegged at 2,160 pounds. That's a lot of force. That can break ribs. You know, when people say, well, I'm looking at 40 calories and I'm going to wear my PPE, and boy, if I have an event, I'm going to walk away, take it off, and go, "Woo, that was a trip." You know, you're wearing your personal protective equipment, but just understanding that it's not just the heat. There's a lot of other things that come out of there, and in that video, and I'm not going to go through slide by slide on every snapshot of that event, but you'll recognize in that video, if you watch it closely, the trough, the cover of the trough became a projectile and hit the worker in his head. Thank goodness that there was a hard hat on there, but it wasn't wearing any other PPE. But in any case, you can have flying debris. Now, this next video that I'm going to show basically takes and adds an overcurrent protective device that's operating and functioning to reduce the incident energy. So the clearing time has been reduced.
There it goes. We got it.
Okay, so now in that video, we know that I have the greater than symbol still on his hands. It's still greater than 437 degrees Fahrenheit, but there was no temperature data on the chest. The pressure on the chest was only 504 pounds per square inch or square foot. And the temperature at the neck was 143 degrees Fahrenheit, and the sound came down as well. So we had visibly in the video, you can see that the sound and everything, the impact was much less. We didn't fill the room with smoke in this event, but we did move that mannequin. Now, in this next video, to really help you understand what clearing time does for us with regard to reducing that electrical hazard and controlling it a little bit, I am now working with a current limiting device. And you're going to see, this is related, if you were in the class on Monday when you saw that cable whip video, we showed how the magnetic forces that a current limiting fuse can take off of the power distribution system and how it reduces the magnetic forces. Well, it does the same thing for incident energy, and this is what you get when you use that type of device.
Interesting.
We had to zoom in on his hands to even give you something to look at, because there not only was it hard to see, but there was nothing to measure. I mean, just look at the amount of energy that we didn't release.
Interesting.
So that fuse cleared in less than 0.004 seconds, and that is huge from an electrical safety perspective. Now, when we calculate incident energy and why we have to understand clearing times, we're using IEEE 1584 to do our calculations. The latest version is the 2018 version. 1584 tells us that we need to calculate three-phase bolted fault currents to understand what's going on, and we have lots of tools on the market available to help us do that. From free tools to tools like SKM, EDSA, Easy Power, all of those different software applications, there is no reason why you can't determine or estimate the amount of fault current at any point in a power distribution system. Remember, even as power systems engineers, we get you in the ballpark. We don't really necessarily want to spend as much time as we could to get you into the exact seat in that ballpark. I mean, I'm basically telling you, when we do studies, I'm going to get you in the ballpark. You may need some binoculars to see Ben Roethlisberger throw that ball, but I could possibly put you right next to him and while he's throwing that ball. But I'll tell you that, you know, we make assumptions. We try to make best case scenarios, worst case scenarios, but there are tools to help you get your job done, so we don't have excuses, and you have resources in suppliers and other engineering firms, etc. So calculating the three-phase bolted fault is critical, and that's what we did on Monday. That's what I love about this program today, is that if you think about this week, Monday we talked short circuit currents. Tuesday we talked about selective coordination. Wednesday we talked about ground fault circuit interrupters and shock protection. We took a little detour into Resi, into AFCIs on Thursday, and then now we're pulling it all together and talking about safe work practices and understanding the hazards, and all of the stuff that we talked about this week is pertinent. Calculate a maximum and minimum arcing currents. We use IEEE 1584 to do that. We understand that an arcing current flows through the air. And if I look at this event, we have a violent explosion. We are vaporizing copper, steel, aluminum, and any of the materials that are in there. I mean, we've basically raised the temperature so high, so fast, that a penny, a copper, the amount that you would find in a penny, when it's vaporized, can fill the volume of a refrigerator. Okay, and you're standing right next to it, and when that event occurs, that ionizing cloud creates that path for current to flow through the air, and that current is actually going through an impedance, because that ionization, that all of that material adds impedance, and it reduces the fault current when it passes through there. So we know for a fact that an arcing current is going to be less than a three-phase bolted fault current, but we will use the three-phase bolted fault current as our starting point, as well as a few other parameters. Again, I can't bring too much with regard to shock, but I can tell you that that what we're talking about here with regard to electrical safe work practices and understanding the hazards from an arc flash perspective, it's really important to understand the mix of current and time, and that time translates into a lot of incident energy. All right, so you guys have a very good handle on recognizing the hazards, and now what we're going to do is I want to show you the. We're going to go to the next question, which is the first choice for electrical work should be to do one of those A, B, C, D, or E. And I'm going to, for my people on WebEx, we're going to show you the results, and we're going to show you the results out there in YouTube land. All right, so here's the results. 69 people said de-energize the circuit. 77 said to establish an electrically safe working condition. Nobody said ensure GFCI protection is present. And you know what? I'm hoping that that is because of our class on Wednesday. Because on Wednesday, if you recall, we basically said that that GFCI is your last resort. That is the last chance. So it should never be your leading indicator. So now we're split here. I got 148 people. I got 77 that say establish an electrically safe working condition. I have 71 that say de-energize the circuit. This is going to take some discussion. I'll tell you that the right answer is that we have to establish an electrically safe working condition. I know I know that it's very important that we follow the right procedures, and we follow 70E, the practice of 70E, and 70E tells us that we have to establish an electrically safe working condition. In fact, there is an entire section in 70E that speaks to that. You know, if we look at Article 100 of the National Electrical of 70E, Article 100, there's some similarities between 70E and the NEC, and the 70E and 70, the National Electrical Code and the Electrical Safe Work Practices both use Article 100 to put all of their definitions. There is a definition for electrically safe work condition, and there's an important reason, because 70E tells us that you just can't turn it off. You have to go through the process to establish an electrically safe working condition. It's a gut reaction of most of us to say, just work de-energized. And my good friend Dim Dollard, Local 98 IBW, he taught me that he would correct me all the time, and I'd get frustrated with him. I never let him know that. Hopefully he's not watching, but because he gets a big head if he does. But in any case, he would say that. He would go, what is it? What was that? I said, you got to work de-energized. He go, well, what is that? I said, establish an electrically safe work condition. I understand the importance of that now, because the more you get involved with this, you have to understand that there's a lot more to just turning it off. What's the definition tells us that we have to put all of the electrical conductors and circuit parts, and you have to disconnect them from energized parts. You need to lock and tag things out. We need to test and verify absence of voltage, and you may, under certain conditions, have to establish a grounding for safety. So I'm just moving some of these contents over here. So shout out to Jim. Yes, thank you. So in any case, it's really critical that we understand that we have a process to establish an electrically safe work condition. Article 120 is titled Establishing an Electrically Safe Work Condition. So it's really important that we understand that 70E even thinks it's so important that it gave it a whole article with its title, and it provides, and Article 120 provides all of the requirements to establish that electrically safe work condition. So it provides the requirements for if you look at how it's laid out, you have dot one is lockout tagout. So you have just the general overview of lockout tagout. You have the principles behind lockout tagout. You have the equipment that you're supposed to use for lockout tagout. You have the procedures. So you have simple procedures, or you have complex. You may have in your power distribution system one overcurrent device or one switch that you need that's supplying the equipment that you're working on. And when you turn it off, you're going to put your lock and tag out on that one piece of switch. But this process really makes it clear that you have to have a one-line diagram. And I have a whole program that I did on that. I believe I did that last week. That was my first little tryout of live streaming. I think it was an hour session. But that was I think it's very important, because a lot of people don't understand. Because here's what happens. Here's what happens with a single line diagram. I've seen it too. I've lived it. You go through the whole project. You created your one-line diagrams. You created your plan reviews, your layouts for the whole facility, and everything is created before you even break ground. So what happens is you get the design process. You actually get into where you have electrical workers, you have construction people out there working. They're installing equipment, and someone says, "Oh, And I had this happen to me on a project. I was the design engineer, and I got a call from the electrician, and he says, "Hey," he says, "would you come out to the job site?" I was a young engineer. I was excited, and I'm like, "Yeah, I get to go into the plant. I got to go through. It was a nuclear plant. I had to put all my hand geometry and get all this stuff to get inside the plant. I get to wear my white hard hat." So I get out there, and I looked out, and I see this big gray box. And I'm like, "Wow, that thing is huge." And he goes, "Yeah." He says, "You like that?" I said, "Yeah." He goes, "Well, you bought it." I'm like, "I did?" He goes, "Yeah, you did." And I'm like, "I don't remember buying anything that big." And he goes, "Yeah." And he says, in fact, on the drawing here, you want me to fit it through that little door over there." I looked at that little door, and I'm like, "Oh, that's," and then I realized what it was. And I'm like, well, it was so small in the catalog when I looked, and I never even thought about the dimensions. Learning curve, right? So we had to make a design change, and we had to make do with the space that we had. We had to reroute some wires. We ended up getting it into the building and all this other good stuff, but it wasn't exactly where I thought it was going to be. So during the actual construction process, your design will change, and it may change. There's a good likelihood that it's going to change. And we have to update our drawings because as you're going to have an electrical worker who's going to say, I need to lock and tag out this piece of equipment because we're working on it. And he's going to pick up that one-line diagram. He's going to look at your schematic diagrams or your layout drawings. And if they're not up to date, he's going to have an issue. And unfortunately, he may or may not know, or she may or may not know that it's not up to date. So the one-line diagram is a critical part of establishing an electrically safe working condition. I will harp on it and harp on it. I was at the NECA's NECA's safety conference, I think it was last year, and they had a program going on where they were teaching people, they had one-line diagrams for a data center, and they were teaching people how they would say, this is what you need to do, this is your task. And then the workers, everybody was sitting around the tables and they had to highlight in different colors all of the different switches they would have to turn on and off because their lockout tagout procedures weren't simple, they were very complex. And you need to identify all of the different aspects of what you're turning on and off. So those exercises with our electrical workers to help them understand drawings, and the design engineers on the phone, the facility people, the people that work in industrials, the industrials that are not on the phone, we're on the web, that are on YouTube or on the WebEx, be mindful that you need to keep those drawings updated. And here's what happens, because I've seen it, I've lived it. You get to the end of the project, the budgets have been spent, there's no more money. You even spent the stuff that the money that was allocated for the updating all of your studies, and it doesn't get done. And you'll have that comment, well, we'll do it next year. No, you've got to make sure that you have the right budget for it and you get it done because lives depend on the accuracy of that document, those documents. 120.5 in 70E talks about the process for establishing and verifying an electrically safe work condition. There are eight steps identified. It's an 8-step process to establish an electrically, there's 8 things that you need to think about. You need to make sure you have that latest one-line diagram. It is critical. I can't say that much. You need to identify the stored energy, understand it. And the reason I say understand it is because I never really thought about it. Even, as an electrical person, we have to remember there may be mechanical stored energy things we've got to think about, not just electrical. There might be something around the equipment that I'm working on that I need to understand a mechanical type of equipment, not just the electrical equipment. Now I'm going to show another video, and I feel confident that it's not going to kill my YouTube stream for my tubers out there. So I'm going to show this video, which it helps demonstrate the charging process on a power circuit breaker or an insulated case circuit breaker, and you're going to see a person charging the handle. And if you ever watch Jurassic Park, you'll see a Westinghouse breaker, an Eaton breaker, where they were charging that handle to open it or close it. That is an important thing that if you opened a power circuit breaker or an insulated case circuit breaker and you charged the handle but didn't close it, it has stored energy. Somebody presses that button, they can close that breaker. So let's watch this, and I'm going to quit talking. And I'm going to play the video somehow. There we go.
So now now we've enabled the arms. That's what the blue light is up here.
You saw that. I'm going to show it one more time in slow motion. He's charging that handle, and then he's going to press that button. And he's going to close that breaker. It's charged. At this point, that breaker is charged and then ready to fire home. Oh, I see what I did. One more time. All right, so that's what he did. He basically established that that he charged that breaker and then he closed that breaker. Once you have that charging arm in there, you will actually close that breaker and it's charged and ready to go. And that's what we're talking about with regard to stored energy. So the right answer to this one was establish an electrically safe working condition. All right, we're going to go to the next question, I believe. All right, so this one is a little bit funner. I'll say funner. The voltage threshold where shock hazards do not exist, or a shock hazard does not exist, is for voltages less than 100, 50, 30. All voltages are hazardous and not sure. So let's take a look and see what the survey says. Survey says that 56 said 50 volts, 70 said all voltages are hazardous, 18 said 30 volts is hazardous. Well, we've got 151 respondents, and looking at some things here, making sure that stuff is working fine. So let's talk about the shock hazard. If you think about what 70E tells us, now I personally, I could be in a couple of these camps, right? I could be in the camp that says all voltages are hazardous for a few different reasons. Even if you are below the threshold of what we categorize as a shock hazard, even if you're in a different threshold there, say it's 15 volts or 24 volts, and I'm on a ladder, right? I could say that the startle factor could knock me off that ladder, right? It could cause me to fall. It could cause a lot of different things that in regards to my safety and in the situation. It'll all depend upon what situation you're in when you are either startled or whatnot. I know there are cases when individuals are in a in that environment of on a what do you call it, a scaffolding. Geez, oh man, I can't even think. When they're on scaffolding and you're in a precarious position, and all of a sudden you feel that tingle. You're an electrical worker. You know that all of a sudden that that you have you've touched something that you probably shouldn't have, and maybe there's some, you're already in that state of mind that says you understand that you could become shocked for whatever reason, and all of a sudden you're sitting there saying, it startles you for that reason. So let's take a look and let's continue on. Let's get you over to. Not sure if I like sharing these things back and forth. Go to 3 and get back with our regularly scheduled program here. Let's talk about. Got a little problem going on my computer, but that is okay right now. Okay, so skipping around, 30 volts is 30 volts is where I have my actually 50 volts is where I have where 70E establishes the hazard with regard to shock. So the key thing to remember is at lower voltages, I can't drive a current through a person's body because the potential's not there. So I'm a little out of sync on some of these slides. But so when I have enough voltage, I can create an arc flash or I can create a shock hazard. If I don't have enough voltage, I don't create a shock hazard. So the key thing to remember there is that the shock hazard begins at 30 volts. I thought I'm almost positive. I don't know why my slides are incorrect here, but you're at a 30 volt threshold per 70E. Let's double check. Gonna go back to the we're going out of sync, so I am flying low. I'm trying to find, I had the code reference here for you, and I'm not finding it. On. Stuffing with my book. Establishing electrically safe work hazard. And I lost my place. All right, well we're gonna come back to that one. The additional hazards. You're gonna identify your hazards. You're gonna look for your normal approach. I'm trying to find the section in the 70E. When you have that section offhand for your shock hazard, please ring it out. Check and see. Yep, 70E is 50 volts. And some of the UL stands. There we go. Qualified persons insulated. So here's where you're at. So take a look. If you have your 70E document, you're in 130.4, and I just had my thumb over it. But if you go over to the restricted approach boundary, that's one area. When you get into the shock boundaries is where you start to discuss the voltage levels. And what you're looking for is the restricted approach boundary tells you that no qualified person shall approach or take any conductive object closer to exposed energized parts in the restricted boundary. And it says, unless one of the following conditions applies, and it says the qualified person is insulated or guarded from energized electrical conductors or circuit parts operating at 50 volts or more. So your 50 volt number is what you're looking for from a 70E perspective. And I believe the confusion part about that is there are some standards that reference 30 volts. So in any case, that restricted approach in that article or section 130.4 that talks shock risk assessment, that's where you're going to find that information. All right. Now, for some reason, my slides, let me just get back to my slide deck here. All right. And these are, so that was not the quite right slides. Let's move into the next question, which talks about those restricted approach boundaries. I'm not sure why I put that those slides in there. So let's take a look at the next question. So the right answer was 50 volts. For those of you on who are on the web, on YouTube, you can see the answer there was 50 volts. For those of you on WebEx, I'm going to share that back over to look at those. And we had 59 say 50 volts. 73 said all voltages, and like I said, I could possibly be in that all voltages are hazard for a lot of different reasons, but 70E does recognize the presence of 50 volts and less being an area where you don't have to worry about a shock hazard. And again, that's just because of how much voltage is present to push it through the body. Now the next question is only under special conditions. Okay, I got them in sync again. The only under special conditions can an unqualified person be within this approach boundary of energized conductors and circuit parts. You have the limited approach boundary, restricted approach boundary, the shock boundary, and not sure. 84 are saying the limited approach boundary. And I would agree with that. The next question, because each of these are in sequence with each other, I'm going to walk through like 3 questions, and then we're going to talk about the approach boundaries. So this one here, the correct answer is limited approach boundary. There are special conditions, and I will go through that language and help you understand the whys. But we're going to have to answer, I think, 2 more questions. The question after this one was, no qualified person can approach or take any conductive object closer to exposed energized electrical conductors or circuit parts in this boundary. So, and I just read that answer, the restricted approach boundary, and again, the restricted approach boundary is in 130.4. 130.4, which talks shock risk assessment, F, as in Frank. And it says, no qualified person shall approach or take any conductive object closer to exposed energized electrical conductors or circuit parts than the restricted approach boundary set forth in table 130.4DA and 130.4DB, unless those conditions, again, you're in that 50 volt range. So 98, look at that. 98, just like local 98. Those guys are okay. Ah, you're gone. All right, so let's take a look at the next question. Get these in sync here. When working around 120 volts exposed fixed circuit parts, my limited approach boundary is one of these. 10 foot 0 inches, 3 foot 6 inches, or not enough information, or I don't know. Well, we had 67 say 3 foot 6, and those are probably guys who have gone through the electrical apprentice training and are very heavily involved with safe work practices, because if you look at the tables, and we're going to talk about this, that you do pretty much have enough information. If you have exposed 120 volts fixed circuit parts, your limited approach boundary is 3 foot 6, and we're going to hopefully understand what a limited approach boundary means. But 3 foot 6 is the right answer, and let's help everybody sort of understand that by walking through this information here. So let's do this. All right. You need to come up, and I'm going to put you guys on WebEx back over to a different screen. All right. We're going to talk the shock risk assessment now. Very important part of the puzzle. Go. Want to make sure everybody is in sync. Okay, let's roll. Shock risk assessment. It's required as part of 110.1. So if I look at 110.1 in 70E, remember, so 70E is laid out very similar to the National Electrical Code. 110 are your general requirements for electrical safety related work practices. So 110 applies generally to all areas. And so this is where you're going to find your electrical safety program. And I always say that we all have an electrical safety program, whether it's written down or not. Just because if you ride a motorcycle, you may not have a piece of paper that says, when I ride my motorcycle, I will wear these personal protective equipment. I will not drive on gravel. I will slow down when I drive around gravel. And there's certain things that you plan on doing. You'll have your gloves, etc. You may not have it written down, but when you get on that bike, you're going to accept a certain level of risk. You may don all of your personal, but you may look like you walked right out of the Harley Davidson dealership, and they outfitted you with everything that you need to prepare for the worst when you're riding a motorcycle. But you may say, I'm not going to wear my pants. I'm not going to wear my gloves, and etc. So, you have a safety plan. associated with it. It may not be the best safety plan, but you have something in your head. It's required as part of 70E. You have to have job safety planning and a briefing. I call this getting your guys' heads in the game. You know, it's just like if there was any sporting event, if you participated in any type of a sporting event, then you are your coach. Or I used to wrestle. My coach would look at me and say, you know, I'd go in and do something really stupid, and he'd yell at me, you know, your head's not in the game. And we have to understand that there's more to the psychology perspective. You know, what was going on last night, the bills we haven't paid yet, and all the different things that are going on in our life are a part of that job and everybody on that job. So we have to make sure that all of our electrical workers are have their head in the game. The job safety plan, again, a qualified individuals. You're going to see that word used a lot in 70E, talking about qualified persons. And the shock risk assessment has to be completed with respect to 130.4, which is an area that 130.4. The title of that is shock risk assessment. We already talked about, and we're gonna go through that in a little bit of detail, not much. There are about these are the different areas in your shock risk assessment. You have your general requirements. You have any additional protective measures that you need to take, all the documentation. You have to establish your boundaries, your restricted, your limited, your shock boundaries, all of these great things, and your arc flash boundaries, everything. You have to understand who can be in those areas, who can't be in those areas. We should be cording those off to make sure that only the qualified people are in an area that we've designated as one of those boundary areas. You have to identify all your shock hazards. So to identify it, we have to understand what is a shock hazard and what isn't a shock hazard. So if you look in Article 100, they define a shock hazard as a source of possible injury or damage to health associated with current through the body caused by contact or approach to energized electrical conductors or circuit parts. So if you think about it, if you come in contact with something, current's going to pass through your body. If you were in the class on Wednesday, you will have experienced the discussion around the path through the body, how much current through the body, and when you come in contact with an energized conductor or part. So, and there are points when you can damage your body. Now, if we look at 130.2, this is, remember 130.4, we had the exception, but this was the section I was looking for earlier. For some reason, my sticky note fell off. 130.2 is where you have, where it says energized electrical conductors and circuit parts operating at voltage equal to or greater than 50 volts. That is, that's your line in the sand. So 50 volts. Now, I know they've done a lot more. They're trying to understand DC a lot more. I've heard 100 volts are on DC, but there's no AC or DC associated with 130.2. It's 50 volts. That's basically what it's telling you, is anything that is 50 volts or greater, it presents a shock hazard. But to those who said all voltages are hazardous, I understand where you're coming from. And even those tingling voltages that may startle you could send you off of a scaffolding or whatever, a ladder or whatever it is that you're on. We have to identify the shock hazards, so we have to understand the equipment. So there's another big area to we talked about the one-line diagrams, and we talked about how important it is to have a single line diagram that's up to date. How about understanding the electrical equipment you're working on? If you're a residential contractor, for example, and you install panel boards every day of the week, okay, you're really good at installing residential panel boards. You come onto my job site, and on my job site, we're at an industrial facility, and you have to work in a low voltage switchgear. You've never seen low voltage switchgear. You may be very qualified to work on a residential panel board, but you're probably not qualified at all to work on a switchboard because you don't understand the equipment. You don't know how to recognize what may be energized, what may not be energized when things are turned on and off inside that equipment. You may kill power to that equipment and enter it not realizing that that equipment has a UPS that has 120 volts running inside the equipment, and not realize that you have another source of voltage because there's a UPS, a battery system inside there to operate relays and things of that nature. So equipment can get complicated, and we have to make sure that we are educated on the equipment upon which or within which we're working. The next part, from once you identified shock hazards, you have to estimate the likelihood of occurrence of injury or damage to health and the potential severity. Shock is shock. The severity is big, um, and we will take steps to reduce the likelihood. What are some of the things that we can do to reduce likelihood? We could put barriers in place. We may put covers over the energized parts so that you don't accidentally come in contact with that. When you put the cover in, you've not eliminated the hazard, you have reduced the likelihood of coming in contact with something. So there's a good debate that I've seen had on the topics of eliminating a hazard as opposed to reducing the likelihood or reducing the severity. And a lot of people get confused or get the terms severity and likely or elimination in mixed up a little bit. But you have to establish and estimate the likelihood of occurrence that you're going to come in contact, or you're going to have an electric come in contact with these contents. So risk assessment. So you have to do a risk assessment, which basically estimates that likelihood of occurrence and injury, the severity of that event. So you may say, I'm on a 2-foot, I'm standing on a step stool, and I could fall. I definitely could fall off of a 2-foot step stool. But my severity to me, if I fall off a 2-foot step stool, might not warrant putting on fall protection and doing all these other good things, because yeah, I could get hurt, but it's not going to be severe. But other areas and other types of work that you get engaged with may have a very high incident of, or a very high potential of severity. You could be death, you could be dismemberment, you could have you can hurt your hearing and leave scars for life, right? These events could be a life-changing event. So you have to do a risk assessment, and Article 100 helps us understand that. And we usually, if I was going to get into depth, there are some good YouTube videos that you can go through and take a look at events that occur and talk about the severity of what you may watch and the likelihood, to help understand what it means to do a risk assessment. I'm not going to do that right now. I'm just trying to raise the awareness of understanding the shock, and understand the fact that we need to be able to recognize when we have a shock hazard, and we need to understand what is an exposed conductor and what is not, and steps we can take to reduce that likelihood. We may not be able to reduce the severity. I mean, if you come in contact on a 120 volt circuit, I could be killed because I'm not protected. But let alone a 480 volt and whatnot. So the best we can do from a shock perspective is either establish an electrically safe work condition, but if we have to do justified energized work, we're going to try to limit our exposure to those energized parts by putting barriers in place, and possibly obviously using insulated tools and gloves and personal protective equipment. Now, the shock protection boundaries are established in 130.4D, and your shock protection boundaries is going to tell you that these are the table in 70E is, I think, even a better example to help us understand what those boundaries are. We have a limited approach boundary and we have a restricted approach boundary. There's our 50 volts, less than 50 volts, and then 50 to 150. That's typically more than likely going to be the area that you work in the most. But you have the limited approach boundary that tells us that no unqualified person can be permitted to approach nearer than what we see in these distances. So this was one of our questions that I took out of this table, basically. So it tells us that if we do have an unqualified person there, you have to have a qualified person or somebody in charge to advise that person. Here's what you're being exposed to. You know, you're coming into an area where you are close enough that you could possibly come in contact with something that is energized, and you're going to have to educate that person and watch that person closely. So if you need somebody in to cross that limited approach boundary, you're going to have to, again, advise that person of what the hazards that are there, and you know, your job is to watch to make sure that person doesn't screw up, right? This is where I heard I've been on job sites where I've had the electrician tell me, put your hands in your pocket. Okay, that was his way of saying, I don't have to worry about your hands as long as they're in your pocket, because I think there's a little bit of Italian in me, and I like to use my hands. Right now, I feel like I'm just projecting in front of a big room here. So, but in any case, you've got to think about that unqualified person and make sure they're aware of those boundaries. This is the most common area that many of us will be exposed to on a more day-to-day basis, almost. You know, anywhere up to about 750, 480 volts. There are probably those on the phone or on the web that are more engaged in that voltage level. A lot of us are exposed a lot to 120 volt circuits. That's typically where we're at most often. Now, in the restricted approach boundary, that's that one way there on the right. This is where you say, no, you can't bring anything that's conductive closer than these distances to the energized parts. You're not going to bring, your hands are going to have your personal protective equipment. Everything is going to be guarded and whatnot. So you have to have your insulating gloves and your sleeves, all of that. You got to think about your sleeves as well. A lot of people have your gloves and they're wearing short sleeves, but you got to remember, you know, you may turn and now your elbow comes in contact with something that's energized. So you want to use barriers, and barriers could be your personal protective equipment. They can be guards that you put up inside that equipment. You need to document that and make sure that you understand, and everybody understands on the job site, what the hazards are from a shock perspective. Now, there's a case example of a scissors lift. I'm not going to show it online, which I think is really important. So let's just think about it before we get to the scissor lift aspect of this. If we excuse me, if we think about, I'm maximizing this, which is probably going to hurt me later. But in any case, you know, when we mentioned the 3'6", look at these numbers right over here. If you have fixed circuit parts, so you're working on an industrial control panel, it's mounted in an enclosure. You open up a panel board cover, you take the dead front off, all of your breakers are mounted. Those are fixed circuit parts. If you are up to 480 volts, actually 3'6" up to 750 volts, up to 750, down to your 50 volt threshold, you are at 3'6". That is your limited approach boundary. Remember, 3'6". You're in an area where you have a panel board open. You've got the dead front off. I personally would put some cones up or put some ribbon up to say, look, here's my 3'6". Nobody's coming over this boundary unless I know that they're a qualified person, or if they're unqualified, I'm going to escort that person, educate them that when you cross this boundary, you are going to be exposed to a potential shock hazard, and you're going to keep them out of that boundary, or you're going to bring them in and you're going to educate them on the hazard and watch them closely. Now, what about the exposed movable conductors? A really good example of exposed movable conductors are your power lines and things of that nature that are energized. They're not insulated, and they can sway with the wind. I may have a conductor that I haven't terminated that could move. That would be an exposed movable conductor. If I have things fixed in place, then I'm at a fixed, and I'm at 3'6". The moment that energized part can move, I'm moving out to 10 foot. And look at this, 10 foot all the ways up to 72.5 kV. So if I have a circuit that is movable, that's a movable conductor for whatever reason, it's not secured in place, it's not terminated on a terminal, it's hanging free, I can be exposed to something because it's movable. My limited approach boundary just went out. Now let's take a look at the restricted approach boundary over here. I have, if it's less than 50 volts, I'm not worried about it. If it's between 50 and 150, so a good example of between 50 and 150 is a receptacle, right? It's a 120 volt item in the power distribution system. My restricted approach boundary, remember what the restricted approach boundary is, I can't bring anything that I bring into that has to be insulated, and I have to have my gloves and whatnot. It says avoid contact. Okay, so I simply have to avoid contact with those energized parts when I'm below 150. And beyond that, I am into 2 foot 2 inches for that boundary. Okay. So when you're looking at a piece of equipment, you've got to know how to identify in here. You know, just looking at this, if you don't know what that equipment is, you see circuit boards, you might make the false assumption that there's no 120 volts in there. It's all less than 50 volts. In fact, there's 120 volts in that piece of equipment. This was taken at an educational event. We walked outside to take a break, and I saw this panel. There was no lock on it or anything. I opened it up, and sure enough, there's exposed energized parts in there. That's a shock hazard. You have to understand that what that is. So you may have kids, you may have other people in and around that area that lift that door and think they're going to touch something in there, and that's a hazard. You open up those transformers, you see exposed terminations like this. That is a shock hazard. Now, if you're looking at a piece of equipment like this is nice. Why? It's the enclosures in good shape. It's like brand new. The bubble cover looks great. The receptacle, the switch looks good. It's got a dead front on it. There are no exposed energized parts there. But now you walk into another facility and you walk into a room and you see this, and you have to scratch your head. You may not know if it's energized or not. Those who are in the facility probably know it's not energized. But you have to treat it all as if it is energized, because you don't have any indications on whether or not you have power or not, because you have to test and then retest to establish an electrically safe working condition. Remember that. You have to make sure that you just don't turn a switch off and say it's de-energized. You have to follow the process of establishing an electrically safe working condition. Same here. All right. Okay, so that was that. Now we're going to get into a different part of the questions. So we went over approach boundaries. I think boundaries are important to understand. And what I like it just from an awareness perspective, if you're taking steps because of that voltage presence to get further away from things and isolate things, it's important that we understand those hazards. Before we get into this one, I'm going to just take a quick look at chat. I think people are learning to use chat. I got the good mornings out there. Last question of the quiz was not representative of all parts of the country. Yes, it was, Wendell. I'm sorry about that. You are all Steeler fans. You just don't know it yet. We have a few mics on. Please mute. Yes, please mute. Correct answer to the question was D, Minnesota Vikings. Ouch. I refused to answer and hit continue. Okay, so there's the sign in. I see you guys are communicating. What is your opinion about arcing fault sustainability for 240 volt single phase panel boards? All right, so here's what we're doing on the single phase. The new 1584, IEEE 1584 did some more testing. And they removed that small transformer. Remember, there was a small transformer size below which you didn't have to do arc flash analysis and etc. We basically in the case of 240, 208 volts, and the single phase stuff, we haven't established the floor. So I'm on the IEEE 1584 steering committee, and I'm on an IEEE 1584 committee as well. But we made a decision to invest some money in to do some testing at single phase to understand exactly, Terry, uh, what what happens at that 240 volt or 208 volt application. So we are going to do further testing to see what the hazards are there. Now, I would say at those levels, you probably have overcurrent devices that are going to act very fast on arcing currents. You're pretty far down into the distribution system, but it is important because we have to understand the arc flash hazard in that area. So as far as I understand, a current limiting device is a fuse or breaker to use to protect another breaker by reducing the fault and then allows the other breakers. Yep. So, that was a question. I thought it was a statement. As far as I understand, a current limiting device is a fuse or breaker used to protect another breaker by reducing the fault. It then, but not completely interrupting it. And then that allows the other breaker to trip and complete. No, not quite right. Not quite right. A current limiting device, the UL standards for overcurrent devices, I'll tell you what, breaker basics and fusology, which is going to come up later. You're going to want to look for those two classes because I'm going to offer those in a 2 hour. We're going to dig deep into this topic, especially. But when I say current limiting, I'm talking that, like in the case of a fuse, you're going to clear that fault within a quarter cycle. So the overcurrent device is going to be tested. It's going to be labeled with current limiting, and it's going to have a certain level of performance. I'm going to have current limiting let-through curves that you will be able to use to understand what the let-through RMS and peak values are. But that overcurrent device will limit the peak and the duration to a specific value, normally less than a half cycle. For fuses, definitely less than a quarter cycle. Now, what you're talking about with regard to a fuse or a breaker protecting another breaker, that is what we call series ratings. When we do a series ratings, that's what you're and that's what you're talking about there, Krista. So remember to sign up for that breaker basics. So what is the DC voltage threshold for shock? That's a good discussion for 125 volt. You know, that the 70E document, if you looked at that section that talked about the shock hazards, it did not say AC or DC. So it's 50 volts in 70E, AC, DC. I know that I've heard 150, I've heard 125, I've heard 100 volts DC. But I can just go by what 70E tells me. What was the answer? All voltages. I think I covered that. Series rated. Yep. So thank you, Don Ganir. That is a series rated system. Show up right ahead of one. Well, I'm looking at the chat session on WebEx, so those on YouTube can't see this. 130.2 electrically safe work conditions. Conductors and parts. Yep. Thank you, Vince Delacroche. 70E, 50 volts, Terry. Thank you. I was struggling there for two reasons. I had three things going on. I had a major issue going on here on my desk. UL says a current limiting breaker is one. Thank you, Don Ganir. You grabbed it right out of the standards. I'm going to end up trying to post these chats. I got to figure out a way to share this with the wider audience. The chat sessions on the WebEx as well. So we're just talking about what current limiting device is. And yes, it's important. Bill pointed out the definition of a qualified person in Article 100 of 70E. Again, I can't stress it enough. It's important to understand all of these terms. And the discussion right now on WebEx is what is the definition of a qualified person? And it is one who has demonstrated skills and knowledge related to the construction and operation of electrical equipment and installations and has received safety training to identify the hazards and reduce the associated risk. So it's one thing to understand the hazards, it's another to reduce the associated risk. Yes. Phase to phase also means leg to leg. In single phase, Yeah, that's phase to neutral, really. In a single phase, it's a phase to neutral. It's not phase to phase because in a single phase, I've got that grounded conductor in that picture. It's really the phase to neutral. I know that definition, Bill, is just one. Okay. Thought it was a great call. Okay, great. Beautiful. All right. So let's take a look at the WebEx stuff that's going on. Because, not WebEx, YouTube. We've got some stuff going on YouTube. Which I don't have anymore. All right. Well, there we go. Okay, so would consider motor control center switchgear cabinets as exposed fixed circuit parts. Yeah, if you have a motor control center or you have a switchgear cabinet, all of those parts in there are fixed. When you land a wire on a termination, Carlos, you have a fixed conductor. But if you have anything that's energized and not secured, or either secured or is like in the case of a power line swinging in the air, that is would be considered movable parts. I'm just looking through some of the notes. DC voltage threshold, we were talked about that. Just repeating my question, 240 volts here. What is your opinion on 240 volts single phase? I answered that one. Thanks, Terry, for hitting both the YouTube. So that's good. Thank you very much. All right, so Ben who? Oh, Ben Roethlisberger. Awesome sauce. Yeah, man, that guy's he's a rock star. Everybody knows it, right? I love it. Let's go to the next question. The following can negatively impact incident energy in a power distribution system. So for the people on YouTube, show you the answer. For those of you on WebEx, I am going to show you the answer. This is what the respondents said. We had 149. We're up to 149. Great. We had 31 say maintenance is not performed on equipment. 98 say all of the above. 16 say none of the above. Oh, I think they're just joking around. Never know though, but that's why we're here. We're here for those 20 and possibly the 99 and possibly the 31. So, everybody has an opinion, and I'm going to give you mine. I understand the ballpark that the all of the above are in. Presence of unqualified people getting involved where they shouldn't be. But in reality, unqualified people are all over the place. I mean, you put me on a job site, woo, radar should go off, okay? Even the most trained individual can be unqualified on certain things. That person who is the residential installer, contractor, he's very qualified for residential, not qualified for switchgear, but he can become qualified. So you can have unqualified people on a job site. That doesn't mean that you have negatively impact incident energy in the power distribution system. So I'm not now in the all of the above ballpark. I'm not in the presence of the unqualified worker ballpark. I'm definitely not in the none of the above. I'm feeling pretty sure. And if an electrical safety program doesn't exist, that really can't impact the incident energy because incident energy is what it is. What does it take what are the two key components of incident energy? Current and time. What impacts incident energy? What impacts the current and time aspect of incident energy? It's how long it takes me to clear the circuit when an arc flash event occurs. So I'm in the presence of maintenance not being performed on the equipment as being the critical piece of that pie. And I say that because again, 70B is all about maintenance, and that, in my opinion, 70B, 70E, and the National Electrical Code fill out what I call the trilogy. That's all three of those devices, all three of those of that equipment requirements working together. So I have to make sure I installed the right products. I have to make sure that I maintain those products correctly. And then I have to follow the safe work practices. But I can't rely on a circuit breaker to clear if I haven't performed maintenance on it. And if that circuit breaker doesn't clear fast enough, then I am into a situation where my incident energy at the location that I'm working could be higher than what I expected. So this is an example of, I would use this as an example. If I'm working at this location in the power distribution system, I'm relying on a circuit breaker up here. But if the circuit breaker that's in this location, that my upstream breaker has never been maintained, has never been operated in years, then I'm into a situation that I don't know if that overcurrent protective device is actually going to do what I'm hoping it does and function and operate. I need to understand what my hazard is and the condition of maintenance of that upstream overcurrent device. I need to be able to recognize the electrical hazard. And I personally, I like my example of your typical transformer installation, right? So your typical transformer installation is something like that you would see in a power distribution system. For those of you on YouTube, that's sort of what I'm talking about there. So that's unfortunately a typical transformer installation, but in reality, what you would hope is that your installation is probably, hopefully, more similar to something like this. You have a downstream panel board, you have an upstream panel board feeding that transformer. To know what's the secondary and what's the primary, I usually look at the conductors. The secondary of this transformer is going to have the primary is going to have a smaller conductor conduit going to it. The secondary is going to have a larger conduit coming out of it just because of the voltage transformation. But to understand the hazards in this application, I really have to understand that next upstream overcurrent protective device is the one that's going to be doing the job, right? So if I'm working on this secondary panel board over here, if I'm standing in front of this panel board and working, I can't rely on the main overcurrent device that's in that panel board. I have to rely on the next upstream overcurrent device, which happens to be in that panel board. Please mute your phones. So the electrical work I'm performing is going to be the clearing time is going to be based on the upstream overcurrent protective device. So understanding where I'm at in the power distribution system helps me understand the magnitude of the hazard that I could be exposed to. Now, if I make a change, or if I look at my power distribution system a little differently, if I add a secondary fusible switch or a breaker in a box, an enclosed circuit breaker on the secondary of that transformer, now my next upstream overcurrent device is that fusible switch. And now I can take credit for that fusible switch, reducing the incident energy considerably. So, maintenance is more than just knowing the maintenance of the equipment. Maintenance could be considered keeping your one-line diagrams updated. So if I think my overcurrent device, my next upstream overcurrent device is a disconnect switch that's on the secondary of that transformer, and I'm relying on that, but in reality, it's more like this scenario where I have everything in one enclosure and my next upstream device is on the primary of that transformer. If I don't understand, if my drawings aren't correct and they're not updated correctly, I could make the false assumption. But having an overcurrent device there, in any case, can extremely reduce the incident energy. So I'm going to run through this quick example of a 250 kVA transformer with 4% impedance. And this is I think, this whole concept here I'm going to share with you is one of the best products that I've seen. That's so simple concept. But in this case here, I have a transformer, a 250 kVA transformer with a 4% impedance. My incident energy at that first panel board is 23.5 calories per centimeter squared. That is a very high. I could tell you the story. I was with a customer and a heavy industrial user. We were having dinner, and I asked him, I said, what is the worst area in your power distribution system, the place where you lose sleep over from an electrical hazard awareness perspective? And his comment was, he says, Tom, that first panel board on the secondary of every transformer in my facility. And you have to ask why. Why is this? And understanding the system here, this breaker that's on the line side of that transformer, how do we size it? We don't size it. We don't size that breaker to protect this conductor. We size this breaker to make sure that I don't trip on inrush. I'm going to follow the code requirements that's going to possibly, if I'm in a selective coordination environment, that primary breaker is going to be up there at 250% of the full load amps of that transformer. But in a normal distribution system where I'm not worried about any coordination, I'm going to have a primary breaker that's probably about 125% of the full load amps of that transformer. Now, that's still, I'm picking it based upon the full load amps at a percentage higher, and then I'm going to size my conductor after I figure out what breaker I'm going to put in there. Now, when I do that, the instantaneous of that circuit breaker is going to be a little bit higher than probably what it would be otherwise during normal, if I just size it for the full load amps. So you combine the transformation of voltage, the through currents are going to be lower on the primary than on the secondary. I have an instantaneous on a breaker on the primary that's a little higher than what I would like it. And now I have a long clearing time, and hence I'm at 23.5 calories per centimeter squared. Now, a small design change means a lot. If I could take that breaker out of that panel board or leave it in and put another breaker in a box ahead of it, and or I could purchase an breaker enclosed transformer where I include all of that in the same transformer enclosure, and now my incident energy is 0.34 calories per centimeter squared. That is humongous to go from 23.5 to 0.34 by simply moving the main breaker out of that panel and putting it in its own enclosure. That is a considerable decrease in incident energy. And now all you've done, right? So I've taken this energy, this 23.5. I had somebody tell me this. I went through this and they were like, wow, all you did was move the energy up there. You didn't get rid of the energy. That is true. I moved the 23.5 calories from the panel board up to this enclosure. Now, what I would ask you is, which will you get in more often? Will you get in this switch, this breaker in a box or fusible switch, or will you get into that panel board more often? I think the answer to that question is you will get into that panel board heck of more often than you will into that single enclosure with an overcurrent device. Or if you were fortunate enough to plan it in place and buy a breaker integrated transformer where you have I'm just going to throw these three letters out there, BIT. If you're a bit head, I've been called a bit head before. You'll love that. My digital world. So that is a world of difference. And if you throw a fuse in there instead of just a fusible disconnect switch, you take that point, you're less than a calorie. You're wearing gloves. You're wearing the minimum PPE. Our goal as design engineers have to be to get our electrical workers into daily wear. That's our goal. I mean, I love the PPE. I love the NSPROs of the world and the all of the guys who make personal protective equipment, but they also make daily wear. And our goal as design engineers, as design build contractors, has to be to get our designs so that the electrical worker is in daily wear. And this is so simple. You take this solution and you look at this. This is also obviously a plexiglass, but it's in our experience center in Pittsburgh. But you've got a transformer, and what they did was they didn't add to the depth, they didn't add to the width, they just made the transformer a little higher, and which is nice because when you're eating your lunch and you put your lunch on that, instead of it's down low, you got to get a nice little bucket you got to sit on to eat your lunch. Now you can stand up and eat your lunch, which standing is good. you have the breaker that's integrated with the transformer. All right, very important, and keep ways to help reduce the clearing times. Using, remember that the time current characteristic curve, and we talked about this on Tuesday in our selective coordination discussions. So you should know, if everybody who was on this call followed through the week, you should know what a time current characteristic curve is, and you should understand that poor maintenance of overcurrent devices can impact these these time current characteristic curves. Now you can say, well, Tom, the fuse guys always tell me there's no maintenance on a fuse. Well, yeah, you can't open it up. You can't do maintenance on a fuse, but you can check to make sure that it's not gotten wet. It didn't get water damaged. There are that the switch that's enclosing it has maintenance been performed on it. Circuit breakers as well. This time current characteristic curve that we use in our coordination efforts is used to establish incident energy. And just think that if I didn't maintain my breaker, and instead of a 0.16 clearing time, it takes a lot longer to clear, I'm adding time to the clearing of my arcing current, which adds incident energy. Maintenance is very important on a power distribution system. You will see limited examples in the National Electrical Code where we talk about maintenance. That is why we have NFPA 70B as in Bob. That talks about maintenance. And we have resources from NEMA, National Electrical Manufacturers Association, that we can download to help us understand what you can and can't do to perform maintenance on things like molded case circuit breakers. But if you don't maintain your electrical distribution system, you can't expect it to respond in the time that it needs to respond. So this is just going through the fact, and this is a good example from a clearing time perspective. So, I've used these slides in other examples. So we know here that for a clearing time of about 0.01 seconds, look, we're in the dirt on this circuit breaker. We're at 0.64 calories, okay, per centimeter squared. That's a very light event. But now if I delay that to 9.6 cycles, I moved it up to 12.7. So if I had a circuit breaker that I didn't maintain and it took longer to clear, I could be dressed for point something calories and actually experience double digits. Or worst case, I'm in, really big double digits. This is 30 cycle delay, 31.8 calories. If I did not do the proper maintenance on my equipment, then I could add time to the clearing, which will increase the electrical hazard. It'll increase the impact of that hazard, the magnitude of the event. It's all about time, clearing time, and current. All right, I got to get myself situated here because we're rolling. We are rolling. We are going to talk about the next question now. These circuit breakers have a handle used to turn it on and off. Oh, I love this. You guys are going to love this one. You are going to love this. Now, I'm going to share the results. You ready for this? Are you ready for this? Molded case circuit breakers, 44 respondents. I had 143 respondents said a molded case circuit breaker. They all have a handle that's used to turn it on and off. Power circuit breakers, I got 4. 89 people said all of the above. I mean, why wouldn't you have a handle to turn off an overcurrent protected device, right? I mean, you think about it. You have to turn it on and off. And what do? We turn the light switch on and off. We use a handle. Why wouldn't you do that for all circuit breakers? I mean, it seems like a logical answer. So those 91 of you, I love you so much, but you're wrong. Yep, it's not all of the above. Those on the 44 in the molded case circuit breaker world that said molded case circuit breakers have a handle to turn them off, I love you. You are correct. Molded case circuit breakers will all have a handle that you will use to turn it on and off. Power circuit breakers, insulated case circuit breakers all have a push button that you would use to turn it on and off. And then you have to ask yourself, why is Tom even caring about that? From an electrical safety, where is the hazard in understanding whether or not a breaker has a handle to turn it on and off? That's a good question. And I'm going to help you understand it. I think it is huge for our electrical workers. And here's why. They have to be able to identify what a molded case circuit breaker is, especially if they're living in a non-labeled environment. You know, I love to say that we will label all of our electrical distribution equipment with incident energy labels, but it is a fact that not all equipment is labeled. And when it's not labeled, the electrical worker has to determine what is his personal protective equipment. So what I'm going to review are the table method in 70E. I'm going to give you an overview of that. And I'm going to give you a little peek into the incident energy analysis method. The table method is what our electrical worker is going to use when they're in an environment that's not labeled. Now, I'm an engineer. I had some issues with trying to understand the table method because I want to talk about arcing currents. I want to talk about clearing times. And my buddy, my good friend Jim Dollar, I mean, we had many heated debates over this and we had discussions. And then one day he said something to me that made sense. I mean, he said a lot of things, but in this case, his comment to me was, he says, Tom, people aren't dying because they're not wearing the right PPE. Says people are dying because they're not wearing any. And we have to give something for our electrical workers to be able to determine what is their personal protective equipment. And he pointed out some really good facts that when I, as an engineer, remember I said it earlier, I'm going to get you into the ballpark, right? I'm going to make assumptions. I make conservative assumptions. I'm going to help and try to figure out, help you determine what the personal protective equipment. I'm going to feel very confident. I'm going to take that incident energy analysis down to 5 decimals and I'm going to slam it home, right? But in reality, all of it is based upon a lot of things that are happening in a power distribution system. I'm taking a best guess. So what I'm going to walk through quickly, I did put that over for everybody. I'm going to walk through what we call the arc flash table method. Primarily because I think it's important that even as engineers, we understand, I know there's a lot of engineers and a lot of industrials that are on the phone or on the web that understand both of these methods. So the arc flash, when you don't have a label, you don't have anything that tells you what the incident energy is and how to dress, you're going to use what they call the table method. And it's a process that that your journeyman, et cetera, are going to use to determine the personal protective equipment. And that's why it is in section or Article 130 of 70E, personal and other protective equipment. Arc flash PPE category method is what it's called. Now, this is a busy slide. I'm not going to dwell on it, but it just talks about that that when it applies, that the arc flash risk assessment is performed in accordance with 130.5 and all this other good stuff. Tells you the tables you need to use, and then you have to apply the for AC equipment, and then there's a DC equipment, etc. So the key thing is this table, and I want to walk you through this to help you understand how it's used. What you see is that there's a table in here that tells you the type of equipment you're working on, right? You can see very clearly that I'm going to know what my arc flash PPE category is, and I'm going to use that to determine what I need to dress in. And then it's going to give me my arc flash boundary, nice and simply. And what I have to do is I have to know what I'm working on. Let's say I'm working on a 240 volt panel board, 240 volts, and I'm working on a panel board. And the next step in this process is I need to estimate the available fault current at this panel board. Now, I have a fundamental issue with not that the table method's a bad thing or anything like that, but I have a fundamental issue with this because I know, and what you'll learn if you come into breaker basics, the more current you give an overcurrent device, the better it works, especially with incident energy. The less current you give it, the longer clearing time you could have. So they put a maximum of 25,000 amps, but if I'm downstream of a fusible switch or if I'm downstream of a 65K breaker, I feed that device current, I'm going to clear faster and I'm going to reduce my incident energy. But hazard to say, I am following 70E here. I'm going to estimate my available fault current at that panel board, as long as it's less than 25,000 amps or equal to 25,000 amps. I'm also going to, it says, what's the maximum clearing time? 0.03 seconds, and I'll tell you how they use it. We know there's notes to this table that tells you a multi-case circuit breaker is going to clear in 2 cycles. An insulated case circuit breaker is going to take more than 2 cycles. A power circuit breaker could take up to 30 cycles, right? So by looking at this, as long as I'm seeing a 2-cycle clearing time, I know I'm downstream of a multi-case circuit breaker. So the way apprentices and journeymen are trained when they're looking at 70Es, they know that as long as I can identify a multi-case circuit breaker, if I'm on a panel board 240 volts and below, I'm in a PPE category 1. If I'm in a panel board that's between 240 and 600 volts and I'm downstream of a multi-case circuit breaker, I'm in a PPE category 2. So depending upon where I'm at, and as long as I don't have more than 25,000 amps, I know exactly how I can dress very quickly. Now, I could probably come up with scenarios that to show, well, look, your instant energy, because the arcing current is so low that it's more than that. But to Jim's point, I need to get people into PPE. That is our biggest chore. So the arc flash PPE category and method is determined in 130.7C15. I have the same picture. So if I'm working over here on this panel board, I'm going to walk upstream and I'm going to look for the handles. If the overcurrent device that is feeding me has a handle, I know I'm in a multi-case circuit breaker. If it doesn't have a handle, if it has those push buttons, because power breakers and insulated case circuit breakers, they have a charging arm. We saw that earlier, and they have a push button to turn it on and off. They don't have a handle. Right. So now I know, okay, say this is a 480 volt panel, right? So that's 480 volts. I am into this guy right here, the second row. Okay. I'm in a PPE category 2, as long as if I estimate the length of the conductor. If there's a transformer in this switchboard, that's feeding this, or if there's a transformer upstream, I can use the Busman FC squared app to estimate my fault current at this panel, and then I would know if it's less than or equal to 25,000 amps, I'm downstream of a multi-case circuit breaker, I am in PPE category 2. That's how they do the table method. I estimate the available fault current at that location. I determine that clearing time from the upstream device. As long as I meet those restrictions, and then to know the clearing time, the new informational note they put in this version of 70E tells us that you get a half cycle fault clearing time for current limiting fuses. And now, this says when the current is in the current limiting region of that fuse. Well, I could say the same thing as long as my current is in the instantaneous region of my breakers. I'm in a 1.5 cycle clearing time for multi-case circuit breakers. Insulated case is 3 cycle fault clearing time. Right? Power circuit breakers, you're moving up 5 cycles, 20 cycles, 30 cycles. So what I do know when I'm looking at this table is anything that's 2 cycles, I'm in a 1 or a 2 category, PPE category. It's nice and easy. And there's my power breaker. You'll notice there's no handle on a power breaker. You have a charging arm in here. Indeed you do. You have a charging arm over here. Indeed you do. But you have push buttons to turn that breaker on and off. A molded case circuit breaker will have that nice little handle sticking out the front. That's how you know you're downstream of a molded case circuit breaker. And you know the clearing times. The faster clearing times are going to give us a lower incident energy. And again, it's all about that trip curve. We're going to cover the breaker basics and understand what comprises how this is all constructed next week a little bit. Again, the higher the current you go, the faster the clearing time. The faster the clearing time, the lower the incident energy. Let the device, when I was a kid, I was always like the manhandling things, and I wanted to do this and do that. My dad would tell me, let the tool do the work, right? Let this tool do its work. Feed it current. Feed it current. And the same thing. So there's your insulated case circuit breaker. Again, there's your clearing times. As that breaker gets bigger, I'm adding more clearing time, right? So as I get into that power circuit breaker, I'm adding more clearing time. I'm delivering more energy downstream. That's the, and then from an incident energy analysis method, we're doing calculations. We're taking into consideration the clearing time. It's 130.5G for incident energy analysis method that we're looking at. And I talked about this already. I believe it was last week, but we have to know the bolted fault current. We have to know the arcing fault current, and based upon the clearing times, determine the amount of energy, and that's going to be dependent upon the overcurrent protective device that you're downstream of. So these are I'm just walking through, the process of an incident energy analysis. It's determine the bolted fault current, establish the arcing current, and the clearing times, and calculate the incident energy. Those are basically your 3 steps to determining. Actually, there's about 5 steps. 5 steps to determine the incident energy. So, and you pick the longest clearing time could get you a higher incident energy, which could be a lower fault current. All right. So we already talked about the clearing time. I already told you. So we already walked through. We already walked through some of these slides. So what I'm going to do now is excuse me, I am going to move into the next question. All right. So now the next question is, if you're not wearing PPE, what are you wearing? You are wearing fuel. That is what you're wearing. So if you're not wearing personal protective equipment, you are wearing fuel. 60 people said daily wear. Yeah, you could be wearing daily wear too. But usually when you say daily wear, it has some sort of arc resistant capability or some sort of flame retardant, all this other good stuff. But what you're wearing is fuel. So the right answer to that one is fuel. And let's talk a little bit about that. Right. Let's do Control 4, Control 3, Q. Queuing you over. All right. So let's move into the our slide deck. Got a little hiccup here, but I'm golden. All right. So if you're not wearing personal protective equipment, you are wearing fuel, and this video is a good example of what we mean by fuel, because it's going to show you what we mean. So if you are not wearing personal protective equipment, you are indeed wearing fuel. Wow, that's just loud. So, and a lot of people make a mistake thinking that, well, the stuff that's not personal protective, it's not, I've got polyester, but it's underneath my PPE. That is the wrong thought process. That could ignite underneath your arc. Say you're wearing an overall, sort of like what this gentleman right here is wearing. He's got his coveralls on. He doesn't have his balaclava on, and he's got 2 people standing right behind him. I want to just share with you. I'm not going to show his video, but if you've never watched the video on Donnie's accident, I would ask you to do that. Donnie basically demonstrated he wasn't wearing his personal protective equipment, and he experienced an arc flash event. His wife created a video. I would ask you, your homework is to go to donniesaccident.com. I wrote an article. I interviewed Donnie, and told his story. But go to donniesaccident.com. It's important that you know his comment was he sat through safety training messages and he never really took it to heart, and it obviously didn't pay off for him, the safety training that he received, because he didn't wear his personal protective equipment. So it's important that we wear our personal protective equipment. All right. Let's get back to the questions. Okay. Control 2 and get the get everybody on the YouTube stream watching that, and let's go and do some more of our questions. All right, the next question. The following hearing protection can be worn when personal protective equipment category 1 is required: earmuffs, electronic actuated ear protection, Bose noise canceling headphones. I know you probably got those for Christmas and you want to wear those. The right answer here is ear canal inserts. Majority of you got those. You don't want to be wearing earmuffs underneath those hoods and things of that nature, because that would be ungood. Take a look at the next question. The National Electrical Code does not have requirements to install arc flash reduction technologies. That is an NFPA 70E requirement. That is false. It does have, and I went over those earlier, I believe, throughout the week. I've mentioned 240.87 and 240.67. Those are both areas where the National Electrical Code includes requirements to reduce incident energy. And so the 36 of you, you need to do your homework. Look at 240.67 and 240.87, 240.87 in the National Electrical Code. The NEC requires all circuit breakers 1,000 amps and above to have an arc reduction technology. Okay, let's think about this one. You 79 said true. Now hold on, let's take a look. Wait, let's go back. NEC does not have requirements. Okay, so it's only 36. We had 102 said false. All right, so 79 said true, but I threw you a curveball. The curveball was it's not 1,000 amps and above. It's 1,200 amps and above. You need to have an arc reduction technology, 1,200 amps and above. That is found in 240.87 and 240.67 of the National Electrical Code. And my favorite football team. We all have a favorite football team, and I know you guys and gals all agree it's the Pittsburgh Steelers. So that is a good thing. I'm glad that we all agree on that one. All right, so let's get back over and talk about. I'm gonna end this. I think maybe end this program with a case study of an IEEE paper that I wrote with a gentleman who was in a, I guess you'd call it like a petrochem facility of some sort. But this is an arc reduction case story where I got a phone call and they said, we had an event and we wanted to thank you for the arc reduction maintenance switch. And, we talk about arc flash events. We talk about all of the bad things with electrical safety, but we don't talk about the good stuff as much as we probably should. And this is the good stuff. So I'll just outline the case here. There was extensive rework being done on a 480 volt distribution system. In the very last part of the project, which included the removal of 3 conductors from this energized gear, you'll see the cubicle that they were working in, and the key message here is that all of this equipment, so this cube, all that, this line here and everything over here was all energized. Okay, this column was de-energized. So in this equipment, there's energized parts and pieces, right? They followed all of the rules when it comes to 70E work practices. They had the pre-job planning and all of the things that they should do. They knew they had 1,000 kVA transformer upstream, 21,000 amps of available fault current. Without an arc reduction technology that we have as a requirement in 240.67 and 87, they were using the arc reduction maintenance switch here. It would have been 17.7. So in this plant, they were either going to dress for a 40 cal or an 8 cal. That's just how they trained everybody, and that's what they did. So in this case, they were wearing the 8-calorie outfit, but they knew they had 2.9 calories of incident energy at this equipment. They did everything that they were supposed to do. They did the lockout tagouts. They did. There was a complex lockout tagout procedures to de-energize, and they activated the arc reduction maintenance switch, which included a lock and tag out to make sure that nobody turned it off. They got everything ready for the work. The arc reduction maintenance switch, which gets them down to a very low value of incident energy. Basically, what it does, it takes this what would have been a short time delay, and it gives it an instantaneous delay. And my marketing people will tell you it's faster than instantaneous because it's an analog circuit. And then they turned that switch on when they did their work, but they couldn't pull the conductor out. So to get the work done, they tried, using the rope that they were supposed to use. They couldn't get the work done, so they went and got a come along that has a metal chain. Now, what they should have done was stopped, renegotiated, and thought about how they were going to do this. They may have finished that job with that come along, but somebody probably would have been in charge of the end of that chain because nobody was. And what happened was the chain dropped down, it went over and into an energized portion of the assembly. Now, that would have been a very large explosion. That's a very high incident energy calculation, and there was intentional delays upstream. But fortunately, the arc reduction maintenance switch took them off without an intentional delay, and the damage to that equipment was little to nothing because they reduced the time. They didn't reduce the current. The current was there. It will always be there because of the impedance of the circuit. But they reduced the clearing time of that overcurrent device, and the damage to the equipment was the size of a dime inside. Right here. These are the little digits. They basically finished the job, de-energized in an electrically safe working state. They changed their shorts and basically did not have to buy new equipment from us. And I told Ken when he told me this story, I said, that is what I want to hear. That's the type of order that I want to lose. I don't want to have to replace equipment because there was an arc flash event. I love to work with people on expanding their facilities and things of that nature, but not because somebody was hurt. Everybody went home safely. They finished that job. They didn't have to replace the equipment. So here's another story from reliability perspective. If I can reduce the amount of damage during one of these types of events, I can increase reliability by getting that facility back up and running a lot faster. You just don't go into your supply house and tell them you need this type of equipment and see if they have it on the shelf. This will take months to get back into shape. And we all know the Steelers, right? So our electrical safety journey is not over. We are still working hard to increase safety. We are making ourselves more knowledgeable and sharing what we know. I see a lot of chat stuff going on. I'm going to take a look at chats. I'm looking at the WebEx right now. Tom, I work in a food industry. We enforce the requirement to wear earplugs. Generally, our workers attach the earplugs to their hard hats. They will probably get knocked off pulling. Is there a better solution? I think that I know that those little strings are nice to have to keep them around your neck. I think the ones without those and putting those inserts inside your ears underneath the hoods will probably be a better. I think stop. And I don't know a better solution other than some of the basic stuff that I would say is just stop. Think about it. Do the buddy system. Just run through the checklist. Are we all wearing our earplugs? Make sure they're in under the hoods and whatnot. Don't have those strings hanging out. Before I've gone over my allotted time, and fade to that. Thank you for tuning in and talking awareness of electrical hazard awareness. And next week I'm going to be doing. Next week I'll be talking about NEC 2020 code changes. I think it'll go a little bit smoother next week than it did this week, especially for the YouTube people, because I figured out the system with regard to not having that delay. And I'm going to work on my questions over the weekend. I will be doing PDH hours again. They'll be doing 2 hours, except for Thursday. Stay tuned for Thursday. Um, I'll let you know how that goes with regard to if I can do a Thursday 12 to 2, or if I might be earlier or later. So thank you for tuning in on YouTube. Thank you for those who dialed in on WebEx. I appreciate that. And for the YouTube individuals, I am going to finally get to do my exit with my little video. So